Welcome back. All right, let's talk about some small stuff. I'm going to try to make this as quick and painless as possible. I know it's not a chemistry class, but just have to introduce a few things and it'll just make, additional material in this unit and later units a little bit easier to understand. Okay? Okay. Small stuff. So let's talk first about matter. This is what was created in the Big Bang, mostly hydrogen and helium. So what is matter? Matter is anything that has mass and occupies space. It's a solid, it's a liquid, it's a gas, it's plasma, it's anything matter. Anything is matter. Matter. This is all matter, all stuff, all right? Or the gas, that's matter. So any physical thing. So let's start there. Now, what about atoms? Those are the smallest unit of matter that retain characteristics of a particular element. And atoms have a nucleus, which contains protons and neutrons, And they have some stuff floating around the outside. Those are electrons. Protons are positively charged. Electrons are negatively charged. Neutrons are neutral. So we have matter, which is all the stuff. Atoms are kind of the smallest unit of matter that retain a particular characteristic of an element. So what are elements? A substance that cannot be broken down into other substances. You can only break it down so much. It's the basic particle that constitutes a chemical element is the atom. So yeah, they all kind of the same thing. Matter is stuff, atoms are stuff, elements are stuff, all right? So it's all matter. Atoms are just the smallest kind of bit of stuff that have a particular set of characteristics of a particular element, okay? If it's confusing, that's fine. We'll kind of move past these terms in a moment. So a little diagram of an atom. You have your protons and neutrons in the center. It's the nucleus. Then you have electrons floating around the outside. Excuse me. Again, atoms are the smallest individual particle that retains the distinct chemical characteristics and properties of a particular element. When I'm talking about elements, I'm talking about the periodic table of elements. More on that momentarily. And atoms the word atoms comes from the Greek word atomos, which means indivisible. It's kind of a cool little thought experiment that they did. I forget who it was and who came up with the idea, but they thought, well, let me get this loaf of bread, let me cut it in half. Let me take that half, cut it in half. Let me take that half, cut it in half. Let me keep cutting. There's going to be a point to where I can no longer cut. Not necessarily physically, but there's going to be some small part of this bread that will be left that will be the essence of the bread. And I can't divide it any further from that. And so even though they couldn't see these things, the ancient Greeks had this thought experiment, this idea about these things that contain the essence of what the larger object is. And that's what atoms are. You take, you say you have a bar of gold, all right? And you keep cutting it in half and cutting it in half and cutting it in half. You're going to be left with one thing you can't cut in half, the littlest thing that still retains the properties and characteristics of that bigger chunk of gold. Whether it's a big chunk or whether it's one atom, it's still the same thing. Again, atoms are made of protons, neutrons, and electrons. So let's fast forward now to elements. So this is a little bit what we'll discuss kind of moving forward in this unit. Not too crazy much. Again, this isn't a chemistry class. I understand that. But, you will hear elements, and usually only a few of them are the more common ones that we find in minerals and rocks. So an element is a substance whose atoms have the same number of protons. So if I'm, for instance, looking at iron, all right, iron has the atomic number 26, the 26th element on the periodic table. That actually indicates the number of protons. So if an element is a substance whose atoms have the same number of protons, any atom of iron will have 26 protons. If I have an atom and it doesn't have 26 protons, it's not iron. Let's say I'm looking at an atom. I can't, they're too small, but let's say I have an atom and it only has 25 protons. Well, guess what? It's not iron. It's manganese. Anyway, so an element is kind of defined by how many protons it has. Hydrogen has 1 proton. Helium has 2 protons. Lithium 3. So on and so forth. That's how this got arranged. Elements can either be found kind of in their pure form or chemically combined with other elements to make compounds. Let's say you're digging and you find gold. Gold is number 79 on the periodic table of elements, so it has 79 protons. Let's say you're digging and you find a chunk of gold. All right, so it's just gold. That's what it is. It's just a billions and trillions of gold atoms. That's it. Right? That's it. But let's say I find salt. All right, salt is a different different mineral, but also a compound. Salt is made up of sodium, which is 11 on the periodic table, and chlorine. So you take sodium and chlorine, mix it together. That's a compound. Makes sodium chloride, which is salt, which is a mineral. So again, a compound is 2 or more elements chemically joined together. So gold, if you're ever lucky to find it out in nature, usually it's in its pure state. It's just gold. That's all that's there. Salt is an example of a compound. And it's this same idea. It's either individual or different combinations of elements creates different minerals. So gold is a mineral, just made up of one type of element. Diamond is another one. A pure diamond is actually just made up of carbon. So it's just made up of a pure element, a bunch of carbon atoms. Whereas, like I said, salt, sodium chloride, or quartz, which is made out of silicon and oxygen, these are compounds. So there's a lot of elements in the periodic table, but lucky for us, the Earth's crust is actually kind of really, it really only has 12 abundant elements and then just kind of everything else. All right. So the 12 most abundant elements in the Earth's crust. Therefore, kind of the 12 most common elements that make up rocks are oxygen, silicon, aluminum, iron, calcium, magnesium, sodium, potassium, titanium, hydrogen, manganese, phosphorus, and then everything else. All those other elements, all those 120 some odd other elements, only kind of constitute 0.77% of the Earth's crust. By far, the most common element is oxygen and silicon, and guess what? When combined, silicon and 2 oxygens, you make silicon dioxide, or silica, which is the mineral quartz. Quartz is a very common mineral. We find it almost everywhere. We find it in almost every rock. Why? Because it's just the most common stuff in the Earth's crust. So since this is what the crust is mostly made out of, then most minerals and or rocks might contain this kind of stuff. There you go. If the most type of clothes I own are hoodies, then chances are I'm going to wear a hoodie. If the crust is mostly made up of this stuff, then the minerals and rocks that come from the crust are going to be made up of this stuff. All right. So, luckily we only have to worry about a handful of elements, not the whole darn table. Okay. One more thing to talk about, because we'll come back to it when we talk about dating and dating techniques in a couple more units. But since we're on the subject of kind of chemistry things, are isotopes. So isotopes are different forms of a particular element. So what you see here, these are all carbon. These are all carbon atoms. These are all the element carbon. However, they're all different. They have some similarities. The reason they're all carbon is because they all have the same number of protons. Remember, the number of protons defines an element. So each of these has 6 protons. So they're all the same thing. They're all carbon. Let's just go back and double check. Yep, carbon, 6. All right, so it has 6 protons. So it's all carbon. However, what an isotope is when the different form of a particular element comes into play when they have different number of neutrons, the other stuff in the nucleus. So in this case, 6, 7, or 8. Because of that, so this So we have what's known as carbon 12 because it has 12 things in the nucleus. Carbon 13, carbon 14, things in the nucleus. So they have the same number of protons, different number of neutrons, but because carbon 13 and carbon 14 have more stuff, they are heavier, and they also have a greater, what's known as atomic mass. And let me go back again. Maybe I should have just kept this. That's what these numbers are down here. The reason they're decimal points, and just kind of a side note, fun fact, I guess, is that it takes into consideration the different isotopes of these particular elements. So normally carbon has 6 protons and 6 neutrons, and so its atomic mass would be 12. But the reason on the periodic table, again, you sometimes see these decimal points, it also is averaging in all the ones that have an atomic mass of 13 and 14, the different isotopes. Okay, so why is this important? Why am I bringing this up? And this is the last thing I'll say about this, is that their isotopes are important in radiometric dating. Mentioned it a little bit in the past unit, the reason we know ages of certain things. The reason we can figure out the ages of rocks and fossils and other ancient organic material is through a process called radiocarbon dating. We'll explain more about that in a later unit, but long story short, you use kind of this fancy equipment to look at different isotopes, see how they're breaking down, and use fancy equipment and science to figure out the rate at how long it takes for it to break down, and then from that you can extrapolate an age of a particular rock or mineral. Now, carbon is really only useful when dating organic material. Remember I mentioned how minerals and rocks, they are not organic material. They are not alive. So you can't use carbon dating. There's other types of dating that we can use. Carbon dating is usually only useful for organic material. So let's say we find an old tree and we want to figure out an old tree that died and was buried in some dirt, and we kind of dig up the dirt and we find this twig or log or leaf in there, and it's still organic material. We can do carbon dating. Right? We can do carbon dating. Or let's say we're hiking around Antarctica and we find a dead frozen penguin, and we want to figure out, how old that thing is. Well, you can, since it's organic, it was alive at one point, you can use carbon dating for that. So anyway, you need to use isotopes. We'll come back to this idea in a later unit. But anyway, quick and painless, I hope. I know this isn't a chemistry class, but we're going to set a foundation, and we'll bring up some of these kind of topics that we talked about in this unit when we kind of further explain minerals and rocks. And minerals is what we got coming up next. See you back here in just a second.